Stanford University.
All right. What I want to do first, I want to go through electromagnetic waves quickly. Just plain electromagnetic, plain meaning P-L-A-N-E, not P-L-A-I-N. Plain electromagnetic waves. How do they fit with Maxwell's equations? What do they look like? I want to do it quickly because I don't want to spend a lot of time at it, but I want to do it clearly. First thing, let's write down Maxwell's equations and put them on the blackboard here on the whiteboard in both their covariant, relativistic form and the non-relativistic form. And then we'll play with them a little bit. There are two sets of Maxwell equations. The first set are identities that follow from the existence of a vector potential, and they're called the Bianchi identities. And they are del dot B equals 0 and B dot, meaning the time derivative of B. If we want to, I suppose I should really write it as dB by dt. This is a vector quantity. dB by dt is equal to the curl of the electric field. Okay. Notice in every one of these equations, incidentally, there is always, and all sides of the equation, all terms, they always come differentiated. That's important. All right, these are two of the equations, and these two equations are the ones which are identities. In the absence, let's take the theory, in the absence of charges and currents, no charges and currents, empty space, then the two other equations are del dot E equals 0, no charges, and an equation that looks like this, except E and B are interchanged, but not quite. So the other equation is dE dt is equal to minus del cross the magnetic field. Those are Maxwell's equations. They have a lovely symmetry. They're easy to remember. Del dot B equals 0, del dot E equals 0, and one of them says that the time derivative of the magnetic field is the curl of the electric field, and the other one says the curl of the time derivative of the electric field is the curl of the magnetic field. The only thing you have to remember is where the sign goes. Okay, and that takes a couple of minutes to work out, but I'll leave it to you. Okay, the equations on the right-hand side can be written in a covariant form, which is called the Bianchi identity. d mu nu of F nu sigma plus d nu of F sigma mu plus, did I get that right? Yes, I did. Plus d sigma F mu nu is equal to 0. This is just a way of rewriting these two equations. Put it over here. And these equations here, which are not identities, which are equations of motion, they would change if you changed the Lagrangian. We haven't introduced the Lagrangian yet, but we will. These equations have the form d mu F mu nu equals, in the case where there are no charges and currents, equals 0. Now, this equation and this equation, both these equations here, all of them, do have a right-hand side that I have not included. This could be the charge density, and on the right-hand side here there would be a current. I've written the equation in empty space. No charges, no currents. There they are. All right, now we want to solve them. I'm going to put this up here, and by solve them, write down a solution. We want to write down a generic form of a plane wave solution. A plane wave simply means a wave proceeding along some axis, and of course we have some freedom. We have freedom along what axis we want to send the wave. All right, but we can always rotate our coordinates. We can always rotate our coordinates so that the z-axis is along the direction of propagation of the wave. Let's do that. The wave is moving, moving down the z-axis, along the z-axis, or is it up the z-axis? Maybe it's up the z-axis, from smaller z to larger z. Okay? It has wavelength lambda equals 2 pi divided by k, where k is called the wave number. And a plane wave of that form, the typical generic plane wave of that form, generally has the functional form sine of kx minus omega t, where we'll have to figure out in a moment what omega is. K can be anything. Fixing k is fixing the wavelength, and the wavelength can be anything. Later on, we will discover that omega must be fixed in terms of k. Omega is determined in terms of k. And each component of the field, electric and magnetic, all 6 components are, you know what, I'm going to change this. I said the wave was going down the z-axis, didn't I? Z-axis. This is a wave going down the z-axis with wave number k, frequency omega. But which components of the field are we talking about? Well, we will assume all components of the field that are non-zero, those which are non-zero, have exactly this form. So let's write out a generic form of this type. The x component of the field as a function of z and t, this is the x component as a function of z and t, we're going to set equal to some number, epsilon x, it's called the polarization vector, but it's just a number, times this same sign, sine kz minus omega t. Incidentally, pay no attention to whether I write upper or lowercase z, it's the same thing. Ey equals epsilon y, a different number, sine of kz minus omega t, Ez equals epsilon z. E here means a function. Epsilons just mean numbers. Same sign, sine k times z minus omega t. Same for the magnetic field. Bx we'll assume as the form, a new set of numbers, we'll call them beta. Beta x sine kz minus omega t. I'm getting tired of writing them, but we'll write them anyway. Beta y sine ky minus omega t. And finally, bz. And I think I'm going to give up and not write it. You know what to write there. Well, I'll write beta z, dot, dot, dot. Okay. Now, first of all, you might ask, how do I know that the magnetic fields and electric fields have both the same kind of dependence? Well, I said it's a plane wave. If I say it's a plane wave, I mean that it's a sine. And I mean all components of the fields are some sort of sine, some sort of waves that look like sines. And this is a fairly generic thing to write down. But you could also write down cosine, right? You could write cosine. I could even do something else. I could make the electric field sine and the magnetic fields cosines. Right. What would happen if I did that? If I did that, we go to the equations up there, the Maxwell equations, and we note that every Maxwell equation, in particular those which relate electric and magnetic fields, think about those. The E dt equals the del cross B. All right? When you write those equations, in each one of them you will be differentiating either with respect to z or with respect to t. What do you get if you differentiate sine with respect to z or t? You'll get cosine. Right? So the left-hand side of any equation of motion will involve a cosine. The right-hand side is also going to be differentiated. For example, the curl operation is a derivative. And so if I differentiate the magnetic field, I will also get cosines, and I'll get something consistent. I'll have that the left-hand side of the equation is a cosine, the right-hand side of the equation is a cosine. Supposing I tried to make the electric field sine and the magnetic field cosine, then I would get into trouble. Differentiating, for example, with respect to time, the electric field would give me cosine. But differentiating the magnetic field would give me sine, I'd be in trouble. So you have to have, if you're going to have sine here, you have to have sine here. Now, I've made a number of conventional assumptions. I've said that the wave is moving along the z-axis. There's no loss of generality there. I just rotate my frame of reference until the z-axis is along the direction of the wave. Okay. I have also, let's forget the relation between electric and magnetic field. I could put cosine, or I could put sine kz minus omega t plus a constant in here, a phase. A sine is a wave that looks like this. Can't I push the wave forward a little bit? Push it up to here? Well, sure I can. I can have a wave that's slightly ahead or behind the wave that I wrote down. But that's a question also of the convention. I will simply, if you want to start with a wave which is slightly ahead at time t equals 0, fine. Just move your z-axis until the z-axis is where the wave happens to be 0. Once you do that, again, the wave gets back to this form here. So this is pretty general. But now I have not in any way used any of the equations of motion. So let's use the equation of motion and see what they say. First of all is del dot, let's take del dot E equals 0. Del dot E, what is del dot E? Del dot E is partial of Ex with respect to x plus partial of Ey with respect to y plus partial of Ez with respect to z. All right, now, Ex does not depend on x. That's gone. Ey does not depend on y. That's gone. I'm supposed to set this equal to 0, incidentally. But Ez does depend on z, and so if I differentiate it, I'm going to get something. But I'm not supposed to get anything. I'm supposed to get 0 on the right-hand side here. The only way to ensure that is to say that epsilon z, for a wave moving along the z-axis, the z component of the field must be 0. Otherwise, the electric field will have a divergence, and that's not allowed. So this is 0. A plane electromagnetic wave moving along an axis does not have any electric field along that direction. Same is true of the magnetic field. For that, we use del dot B equals 0. Same thing. This is also equal to 0. All right, so we've used up the del dot equations. Now how about the other equations? Let's see what they say. All right, let's pick one. Let's take the E dt. Oh, one more thing. Yeah. This epsilon x and epsilon y are constants. They don't vary. They're just numbers. All right? They're vectors in the xy plane. They're vectors in the xy plane which determine, roughly speaking, the ratio or the amount of Ex and Ey that's there. You can always rotate in the xy plane. The wave is going that way. You can always rotate your axes, the xy axis, until one of these is 0. For example, you can always line up your x-axis so that Ex is not equal to 0, but Ey is 0. These here are a little two-dimensional vector in the xy plane, and you can always rotate your coordinates so that one of the two components is equal to 0. That's, again, no loss of generality. Just remember that we've used up whatever rotational freedom we've had to set this also equal to 0. I cannot do it yet for the magnetic field. I don't know what this implies about the magnetic field. We'll find out in a moment. So this is my starting point, an electromagnetic wave with an electric field that points along, let's see, the x-axis, and which oscillates as it goes downstream or upstream. Okay, let's now use the E dt equals minus del cross B. The E dt equals minus del cross B. And there's only one component, well, there's two components of it that we have to worry about. It's a trivial matter to see that the z component of the equation is trivial. Let's look at both the x and y components of this equation. First of all, the x component. The ex by dt is the x component of minus del cross B. What's the x component of del cross B? That's equal to minus dy bz minus dz by. All right, so now we have an equation relating the ex dt to bz and by. But bz is 0. We've already said bz is 0. So we get rid of this, and we just get plus. The ex by dt is the by by dz. Now the first thing it tells us is that by cannot be 0. We set ey to 0, but now we find out that by cannot be equal to 0. In other words, the electric and magnetic field cannot be parallel to each other. You cannot have a situation where by is not equal to 0 if where by, you know what I mean. Okay, so the ex by dt, so let's plug in now. The ex by dt, that's just differentiating that. That gives us epsilon, I'll just call it epsilon since there's only one of them, let's just call it epsilon. And now we want to differentiate with respect to time. That gives us a factor of minus omega with differentiating sign times cosine of omega of kx minus omega t. Everybody follow what I did? I just differentiated this with respect to time. The time derivative gave me a minus omega, and that's what we have on the left-hand side. Say it again? Okay, right, thank you, kz. Right. Now we're going to differentiate by. Here it is. And that's going to equal, must be equal to beta y times k. We're differentiating with respect to, what did I write here? I keep writing the wrong letter here. Kz. by, they're all kz. Times k times, again, cosine. All right, the cosines cancel, and what we find is an equation that by, here it is, by, cosine cancels, by is equal to minus epsilon x omega over k. by is equal to minus epsilon, this was epsilon x, omega over k. That's one fact. Okay, a second fact we can get by applying the same equation to the y component. Let's work out the y component here. All right. So here we have the ey by dt, but that's 0. We've said that ey is equal to 0. What do we get on the right-hand side? The right-hand side has dxbz minus dz bx. Now, do I have the sign right or do I have the sign wrong? It doesn't matter. It's either dx bz or d, this is, let's see, this is the y component of the curl, which means, I think I have the sign right here. But it hardly matters since the left-hand side is known to be 0. It says the right-hand side is 0, but bz itself is equal to 0. And what is this going to tell me? If I plug in bx, the only way it can be 0 is if beta x is equal to 0. All right, that's the only way that this can be equal to 0. When I differentiate bx with respect to z, I'll get something non-zero unless beta x is equal to 0. So this equation tells me beta x is equal to 0. And what does this say? This says that if the electric field, let's draw some coordinates now. Let's draw a picture of this wave, what we know so far. Here's our x-axis, our y-axis, and our z-axis. And the wave is moving along the z-axis, so it's a sine wave, moving along the z-axis. What this tells, and we've assumed that the electric field points along the x-axis. Okay, so the electric field looks like so. At a particular instant of time, it looks like that, and it moves. It moves, of course, with the speed of light, which we've set equal to 1. I've assumed we've set equal to 1. So that's the electric field, E. And what these equations tell us is that the magnetic field lies along the y-axis. There's no component along the x-axis, has only a component along the y-axis, so it looks along the y-axis. It's also a sine wave. I'm trying to draw this in a sort of three-dimensional way. Think of the magnetic field as lying along the y-axis, oscillating as you move down the axis, and the electric field along the x-axis. So the first thing you learn, well, maybe not the first, but another thing we've learned, is that the electric and magnetic field are perpendicular to each other, and they're also both perpendicular to the direction of motion of the wave. Okay. The words for that is that the electric and magnetic fields are transverse. That means they're perpendicular to the direction of motion of the wave. All right, there's one more piece of information. Here we used the dE dt equals del cross B minus del cross B equation, and we got a relationship between beta and epsilon. Getting rid of the indices here, there's only beta y is non-zero and only epsilon x is non-zero, so we can write this just in the form beta is equal to minus epsilon omega over k. That's the equation that comes from the dE dt equation. There's also the dB dt equation. It looks exactly the same, has exactly the same structure, except for a minus sign, and B and E are interchanged. With no further work, I can write down the corresponding equation. Just interchange beta and epsilon and change the sign. And all it says is that if you do it right, you find out that the other equation is that epsilon is equal, I think it's also minus beta omega over k. There's a couple, there are two signs. The two signs conspire, I think, to give you the same relationship. What does that tell you about epsilon? What does that, what does that tell us? it tells us, do I have it right? Epsilon is what I wanted to say is that omega, oh yeah, oh, omega over k equals 1. Yeah, I was having trouble getting the words out. It says that omega over k is equal to 1. It says it's the inverse of itself. It says omega over k is k over omega. The only way omega over k can be k over omega is if omega equals k. All right, so that's the last piece of information. No, they don't if c is 1. Right. If c is 1, they don't have different units. Right. This has, omega has units of inverse time, k has inverse distance, and distance and time are the same. All right, so that tells me then that I can simplify this and just write it as sine of kz minus kt, or just sine of k times z minus t, everywheres. Just sine of k z minus t. Now, where would the speed of light go into this? K times z minus t. Well, it's, of course, the speed of light would go right where it needs to go in order to make the units correct. So the speed of light would go over here. Maxwell's equations do have speeds of light in them. I've left them out because, you know, when you're doing relativity, you don't want to be bothered with c not being equal to 1. Okay, so that's an electromagnetic plane wave. It's transverse. The electric and magnetic fields are equal to each other but orthogonal. The magnitude of the electric and magnetic field are equal to each other, epsilon equals beta. They're orthogonal to each other, and the whole blooming thing moves down the axis sort of rigidly. Yeah.
Question. Are the electric magnetic field always in phase with each other, or can be out of phase?
In a plane electromagnetic wave, they're always in phase with each other. Circular polarization is a little more tricky, but we'll do plane waves. Yes, they're in phase with each other.
This is semantics, but doesn't the minus sign make them 180 degrees out of phase?
Oh, yeah. That's, yeah, but they're not 90 degrees out of phase. Right. You can't, right. That's right. Okay, that's electromagnetic fields.
In phase, is energy conserved?
Yeah. Energy is conserved.
The fields go from maximum simultaneously to zero simultaneously.
Yeah. Right. But the energy that was over here just moves to here. It's not that the energy isn't conserved. True enough, the energy density at a point changes. The energy density is related to the square of the electric and magnetic field. So if you stand at a point, the wave goes by you. First you see some energy, and then you see no energy, and then you see some energy, and then you see no energy density. But the total, the total amount of energy over here, after a little while, is just replaced by energy over here. A little later, it's replaced by energy over here. The only other thing you need to know about electromagnetic waves is that you can add them, you can choose epsilon to be any number you want, big or small. Beta will follow. And you can add waves or subtract them, even in different directions. And you still have a solution to Maxwell's equations. All right, I wanted to go through that because it's kind of a little ridiculous to teach a course in electromagnetism and not write down the electromagnetic plane wave, which I suspect many of you have seen before, so I was pretty quick about it. Now we want to get on. Yeah.
When you assume that E and B have the same phase. And
No, I don't. No, I don't need to assume they have the same phase. That's the statement that both sides of the equations involve a derivative. So when you differentiate E and set it equal to some other derivative of B, you can't afford to have a phase difference here and here. Right. Yeah.
I'm sorry, I missed your argument on why that last equation, epsilon equals minus beta omega over k. The second one there, you're looking at it right now.
No.
The top one, I saw we derived that because,
How did I get to this one?
yeah.
Oh, just by noticing that the other equation up there has exactly the same form, except B interchanged with E. Right. All right, I'll let you go through that in detail. It's easy. You know, it's fun. The Lagrangian. As I've emphasized over and over again, all of the ideas of energy conservation, momentum conservation, relationship between those conservation laws and symmetry laws follow only if you start with the principle of least action. You can write down all sorts of differential equations for various kinds of things, and there won't be energy conservation. There'll be no energy to be conserved unless those equations are derived from a Lagrangian, from an action principle. So since we are inclined to deeply believe in energy conservation, we should be looking for a Lagrangian formulation of Maxwell's equations. Okay, so let's go through the principles and see if we can make our best guess about what the Lagrangian is. And then what we want to do, the first set of equations on the left, those are identities. We don't need to prove them. They just follow from definitions. We want the second set of equations, which let's add the right-hand sides to them. Let's write it this way. This is equal to rho, which is also equal to the time component of the 4 vector of current. And now let's put this on the left-hand side of the equation, and then the right-hand side of the equation is the current vector, the space component of the current vector. This is a vector, this is a vector, that better be a vector. And on the right-hand side, in the covariant equations, this just becomes J nu. The time component of this equation, J naught, simply gives you this one, and the space components combine and conspire to give you the other Maxwell equation. Okay, how do you get these equations from a Lagrangian? So let's start with some principles. The first principle is locality. Oh, you know, I'm gonna take a digression first before. No, we're okay. All right. Locality. Again, that means whatever's going on at one instant of time is only related to a neighboring instant of time and a neighboring position. And that's always guaranteed if the action is an integral. In the case of a particle, an integral along the world line. In the case of a field theory, an integral over 4-dimensional space, dx, dy, dz, dt, or d4x, of a Lagrangian density, where the Lagrangian density depends on all of the fields, however many fields are in your theory. Let's just call them phi for the moment. They're, of course, going to wind up being the vector potential. But for the moment, let's just call them phi. There could be several of them. I won't write several of them. Phi will stand for whatever fields exist. And also derivatives of phi with respect to space and with respect to time. I'm going to use the notation that the derivative of a thing with respect to x mu, sometimes I'll just write it d mu phi, But other times I'll use an even more condensed notation, phi comma mu. That's a standard notation. A comma means derivative, and sub mu means derivative with respect to the muth component of x. This is a standard notation, and I will use it. So, locality says the Lagrangian depends on phi and phi mu. Same phi, phi comma mu. Now, this doesn't mean one particular derivative. It means all of the derivatives. Phi mu is a generic symbol here. It means time derivative, space derivative, all the derivatives. That's the condition, basically, that the equations of motion are differential equations that relate things locally. Next condition. Next condition is Lorentz invariance. Lorentz invariance, that's simple. The Lagrangian should be a scalar. It should not depend on which frame of reference it's evaluated in. Okay, it should be a scalar. So for example, for a single simple scalar field, let's just go back over it again. For a single simple scalar field, you can write down lots of different things, but some simple things would be Lagrangian contains, for example, it could contain any function of phi. Phi is itself a scalar. Any function of phi is a scalar. So, let's see, what did I call it in my notes? Either u or v, I don't remember. U of phi. It could contain u of phi, any function. And it can contain, and it must contain, derivatives. Otherwise, it's not a very interesting Lagrangian. So it could contain things like, it can't contain dx phi by itself. That would be nonsense. That's not a scalar. That's the x component of a vector. You can't put dx phi in and expect your Lagrangian to be, it can be in the Lagrangian, but not just in this simple form. What you can have is d mu phi, or which is the same as phi comma mu, phi comma mu. And what's the difference between the upstairs index and the downstairs index? Does it mean anything to put this index upstairs? It's just a change of sign for the time component. So for example, this object here, which is a scalar, is really minus phi dot squared plus dx phi squared plus dy phi squared and so forth. It's just this change of sign of time relative to space. So assume you know about that. This could go into the Lagrangian. It's a good scalar. And by convention, this is really more of a convention than anything else, we put a minus 1/2 there. So, Lagrangian for a simple scalar, this is not the only thing you could write. This is just a simple thing. Lagrangian could be minus 1/2 d mu phi minus any, oops, this should be a minus sign here, minus any u of phi. That's, as I said, that's not the most general thing you can write down. Many, many more things, but this is a simple Lagrangian. Last thing, before we go on to electromagnetism, let's just recall how you go from the Lagrangian to the equations of motion. Right, these are the Euler-Lagrange equation. For each field, now I've only written one field here, but there could be several fields. We might add the Lagrangians for several different fields together. We might even put them in a more interesting way that mixes them together in various ways. For each independent field, in this case only one of them, we begin with the partial derivative of the Lagrangian with respect to phi comma mu. Derivative just means this derivative here. And then we differentiate that with respect to x mu. That's the left-hand side of the equation. The right-hand side of the equation is the derivative of L with respect to phi. This is the immediate analog of the Lagrange equations of motion for a particle, which would read d by dt of partial of L with respect to the time derivative of a coordinate is equal to dl by d time by coordinate. All right, so what does this give? I'll let you work it out. It's very easy. It just gives you, we've done this before, this gives d second phi by dt squared minus d second phi by dx squared. I won't bother writing y and z. Dot, 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 y and z is equal to minus du by d phi. All right, simple wave equation. We've done this before. I wanted to remind you because we're going to do exactly the same thing, exactly the same process with the vector potential. It's more complicated. I'll try to do it in the simplest way that I can. You know, it's got more indices floating around. One more principle: locality, Lorentz invariance, and when it comes to electrodynamics, one more principle: gauge invariance. So let's put gauge invariance here. For the moment, let's set the current equal to 0. No charges, just electromagnetic field. Gauge invariance tells us the Lagrangian, or at least the action should not change when you make a gauge transformation. Right? The simplest way to ensure that is to make the Lagrangian itself out of things which are gauge invariant. The things which are gauge invariant are F mu nu. The electric and magnetic fields. The electric and magnetic fields are gauge invariant. They don't change when you add to A and since the electromagnetic field F doesn't change when you make a gauge transformation, anything that you construct out of F will also not change. Right? One thing you can't put in, is there something you can't put in? All right. For example, you can't put in A mu. Why not? This is a scalar. It's made up out of the fields. Incidentally, these mu's here don't mean derivatives. These are the components of the fields A. If I wanted to differentiate, I've got to put that comma in. The comma indicates derivative, and I'll try to be careful about it. This just means a naught squared minus, or ax squared plus ay squared plus az squared minus a naught squared. This is a scalar, perfectly good Lorentz invariant, but it's not gauge invariant. If you shift A in this way, this quantity would change. So this is no good. Can't put it in. Illegal. Not gauge invariant. You can put in any component of F mu nu in any way that you like as far as gauge invariance goes. But as far as Lorentz invariance, you've got to make a scalar out of it. So how do you make a scalar out of F mu nu? Well, there's a number of ways. The rules are always the same. Contract indices. If you have two lower indices, if you have a tensor, some general kind of tensor, T mu nu, and you want to make a scalar out of it, you raise one index, and then you contract them by setting the indices equal and summing. That's the general rule for making scalars out of tensors. What would happen if you tried that with f? That would equal f mu mu. No, sorry. What about taking f mu mu? What is that? Okay, so what is that? It's 0. The reason is the following. All of the components of f are such that the diagonal components are 0. f11 is equal to 0, f22 equals 0, f33 is equal to 0. Raising this index here, the second index, that doesn't change anything. It just changes the sign. But the sign of 0, 0 doesn't change when you change its sign. f11 is 0, and so forth. So taking f mu mu, which means f naught naught plus f11 plus f22 plus f33, that's just plain 0. Nothing there. So that's not a good scalar to put in the Lagrangian. Just doesn't, it's just 0. What else? Is there anything else we could put in? I thought I wrote down a couple of things, but well, the first non-trivial thing that you can write down, by first I mean the lowest order in f. Nothing linear in f works. You can try things which are quadratic in f, and then you get something. You can have f mu nu, f mu nu. That means something and it's not 0, and let's see what it means. Let's see if we can see what it means. Let's see if we can work out exactly what this quantity is. Okay. First of all, there are the mixed components, space-time mixed components. There would be f naught n, f naught n. Right? That's where mu is naught, time, and nu is space, n. What does that equal to? That's almost the square of the electric field. The mixed components of f are the electric fields. The only reason it's not the square of the electric field is because to raise the time component, you have to change the sign. So this thing here is equal to minus the electric field squared. So that's one kind of term that appears in here. F naught n, that's where mu is a time component. Now, actually, this term appears twice. It appears twice because you can have mu be the space component and nu be the time component. Right. Here we had the first index being time, the second index being space, but there's the opposite possibility. The first index being space, the second index being time, and that just gives us twice the same thing. All right, so first of all, this contains minus twice the electric field squared. But what else? It also contains space components. For example, f12, meaning xy, fxy times fxy. 1, 2. Raising space indices does nothing. What is f12 in terms of electric and magnetic fields? It's B3. Z, x, y, z, 1, 2, 3. All right? So there is plus bz squared. But of course, all possibilities enter. B1, 2, which enters twice. It enters because there's f12, f12, and also f21, f21. So there's twice b squared. And that's what it is. It's twice e squared minus b squared. It's twice b squared minus e squared. Okay. Again, there's a convention. When I say there's a convention, I mean it would affect nothing if I didn't do it. It would not affect the equations of motion, but somewhere along the line, people started with definite conventions about the Lagrangian. The convention is such that the Lagrangian begins with plus e squared minus b squared. In other words, there's a minus sign. I would make this plus. Let's make the equation correct, first of all. Mu nu, mu nu. Okay, first of all, conventionally, one puts in a minus sign so that the electric field comes in with a positive sign. E squared minus b squared times a factor of 2. Again, the factor of 2 only occurs because each contribution appears twice. F12 times F12 and F21 times F21. They're both the same thing. All right. Second, as part of the convention, is a factor of 1/4, minus 1/4. And that makes this a half e squared minus b squared. Again, there is no content in it other than to make it consistent with ancient conventions, the minus 1/4 here.
What about F00? Is that 0?
That's 0. F0, 0, all the diagonal elements of F are 0. F11, F22. So they're only the off-diagonal elements. The off-diagonal mixed space-time components, those are electric. The space-space components are magnetic. All right, so that's the Lagrangian E squared minus B squared. It's Lorentz invariant. It's local. And it is, in many ways, not only the simplest thing you can write down, it's also the correct thing for electrodynamics. It gives rise to exactly these equations. For the moment, I have not included J. Okay, so let's see if we can see that. It's a little bit of a nuisance, but not too bad. I'll try to take you through it reasonably simply. First of all, what are the fields? Let's write down the Euler-Lagrange equation again. Euler-Lagrange, here it is. EL equation. For each field, and write down first the derivative of the Lagrangian with respect to phi comma nu. Right. Then differentiate the whole thing with respect to x nu. Set that equal to the derivative of the Lagrangian with respect to phi. For each field, you write a separate equation like this. Now, what are the fields that I'm talking about? They are the vector potentials, A0, AX, AY, and AZ. 4 distinct fields. Sorry. Let's stick to either X, Y, and Z or 1, 2, and 3. All right, those are the independent fields. Again, these indices here do not correspond to derivatives. What about derivatives? Let's introduce a notation for derivatives of the fields A1, A2, and A3. Well, you can have the muth component of the field differentiated with respect to the nuth coordinate. A mu comma nu literally means the derivative of A mu with respect to x nu. What about the field tensor in this form? The field tensor, where let's write it down over here. Here's the field tensor. F mu nu equals the A mu by dx nu minus the a nu by dx mu, which is the same thing as a mu comma nu minus a nu comma mu. Okay, you got the notation? It saves writing a bunch of partial derivatives, fraction bars, x's. We just simplify. The comma means derivative. Okay, so now we can write down the Lagrangian and try to work out the Euler-Lagrange equations of motion. In working out the Euler-Lagrange equations, we take the four components of A to be independent separate fields. Okay, so there'll be a field equation for each one of them. All right, so here we have it. Minus is L. L is equal to minus 1/4 A mu nu minus A nu mu, that's F mu nu, times the same thing again. Oh no, we have to put the index upstairs. We have to put the indices upstairs. And again, I have emphasized over and over, the only difference between upstairs and downstairs is a sign change when you move a time index. That's all. That's the Lagrangian, minus 1/4 F mu nu, F mu nu. Let's see if we can work out the field equation, and let's pick a particular component of A. This is all there is. That's it. That's the Lagrangian. And you can write it out in detail if you like in terms of derivatives of A. The things which correspond to phi are the A's. And so we should now work out the Euler-Lagrange equations. There'll be an equation for each component of A. So pick a component. You mind if I pick, what did I pick here? It won't matter, they all work the same way. Yeah. Let's work out the equation of motion for the component A sub x. A sub x, or what's the same thing, A sub 1. Let's see if we can work out the equation of motion. The first thing we have to do is we have to compute partial derivative of L with respect to A x mu. That's the analog, where is it? That's the analog of this object over here, except where phi is given by AX. And then we have to differentiate it with respect to x mu. But let's do that later. We'll do that in a minute. So what we need to calculate is the derivative of the Lagrangian with respect to specific derivatives of specific components of A. Let's take an example. Derivative of the Lagrangian with respect to A x comma y. That's a fairly generic, this is the derivative of the Lagrangian with respect to A x comma y. Everybody understand what that means? You look in the Lagrangian, you look for ax comma y. That means the derivative of ax with respect to y, and you differentiate the Lagrangian. Okay, where are we going to find axy in here? Basically, there's one term in the sum over mu and nu. It's axy minus ayx times axy minus ayx. Right. So let's write down what we get. Let's see what we get there. What we get is minus 1/2. I'll tell you why 1/2 in a moment. Derivative of ax with respect to y minus the derivative of ay with respect to x squared. There are lots of other terms in the Lagrangian, but they do not contain AXY. There are other terms, but they do not contain AXY. Now, why do I have a half here instead of a quarter? Because there are two terms. There are two terms. There's one term in which mu is x and nu is y, and there's another term in which mu is y and nu is x. So you basically get two terms for each combination mu and nu. All right, now let's write this out. Let's write this out in some detail. Minus a half, put a big bracket around it. This is ax comma y squared. I've squared this. Now there's the cross term minus axy ayx with commas in the right place. Twice that. I think I better clean that up. Not very clear. Let's try it. Equals minus 1/2 derivative of a. Let's use the condensed notation. Ax comma y squared. Just coming from squaring, just binomial theorem. All right. Then there's minus twice the axy ayx. And the last term is plus ayx squared. This is the only term in the Lagrangian which contains ax comma y. It also contains other things, but it's the only term which contains axy. So far, this is the term in the Lagrangian that we're interested in. Now I want to differentiate it with respect to this particular component. It appears here. Let's circle the places where it appears. It appears here, squared, and it appears here multiplied not by itself. Axy and ayx are different objects. This is derivative of ax with respect to y. This is derivative of ay with respect to x. They are different objects. We're searching out the dependence on axy. Okay? So what's the derivative of this Lagrangian with respect to axy? Very simple. We just the derivative of L with respect to axy from here is minus axy. What happened to the factor of a half? It's just this is squared. So when you differentiate the square of something, you get a 2. All right? So this is axy. And now we also have this one over here, which gives us minus. We're differentiating with respect to axy. That gives us ayx. So it gives us plus ayx. It took a long time to get there, but the answer is very, very simple. The derivative of L with respect to axy is just minus fxy. Derivative of ax with respect to y minus derivative of ay with respect to x is fxy. So it was a long haul, but let me write down the general formula. Oh, incidentally, this is also equal to minus fxy. Space components can go up or down for free. So let me write down now the general formula. The derivative of the Lagrangian with respect to a mu comma nu, that's what we're going to need. That is equal to minus f mu nu. If we went through the same exercise and did it for every component, we would discover that differentiating the Lagrangian with respect to the derivative of a with respect to nu would just give us f mu nu. What's the next step? The next step is right over here. We differentiate the Lagrangian with respect to phi mu and then differentiate again. Okay? So, d by dx nu of dl by dA mu comma nu. That's just minus the derivative of f mu nu with respect to x nu. That's what's turning up here. Right? Differentiating with respect to x nu just gives us the left-hand side of Maxwell's equations. Now, what else is there? Well, it's the derivative of the Lagrangians with respect to the fields themselves. That would mean the derivative of the Lagrangian with respect to undifferentiated A. But undifferentiated A doesn't appear in the Lagrangian. So that's it. That's all there is. The Euler-Lagrange equation is that this is equal to 0. All right, that is and that's it. That's the whole story. It looks much more complicated than it is. You just take f, so the squares of all of the elements, and that's the Lagrangian. From it, you work out the Euler-Lagrange equations, and it's just two of the Maxwell equations. The two of the Maxwell equations that happen to have the j's on the right-hand side, we haven't included j for the moment. All right. The other Maxwell equations, we don't have to do anything. They're identities that follow from the definition of A and its relationship to F. Any questions up till now? This is not hard, but you'll have to sit down and do it. You have to sit down and do it, work out the details of it, because I'm sure it doesn't help to watch me do it. I have no doubt that it doesn't help to watch me do it. Even if you manage to follow what I did, you will forget it in 5 minutes, but you won't forget it if you go through the steps yourself. Yeah?
The very top equation on the top board of it,
Yeah.
when you set that equal to minus 1/2, the difference in those
Yeah.
derivatives.
Squared.
Squared. What's going on there? Are you assuming that the B field is in the Z direction only? Or
No. Oh, I'm sorry. Yeah. In writing this over here, no, I just pulled out one term. I just pulled out one term. No. Plus dot, dot, dot. Sorry. Plus dot, dot, dot. Yeah, good. Plus dot, dot, dot. I just pulled out one term for examination. Yeah.
You use two special coordinates as an example. If you used one at a time component.
You would have gotten the same sort of thing. You would have found dl by d, let's call this naught here, and this m would have been fm naught, which would have been a certain component of the electric field. When I use two space components, I get a magnetic field. When I use one space and one time, I get an electric field.
And like the reason it doesn't change sign when it goes upstairs?
If you keep track of the signs carefully, you'll find that this is general.
Push your two time components to cancel out or something?
Yeah. Go through the indices, and you'll find out that they cancel out.
Question?
Yeah.
There, it's covered now, but where you wrote gauge invariance?
Yeah.
You said that you were setting that j equals 0, so are we still?
I did for the moment, but now I want to come back to it in a minute.
So we're still, okay.
Yeah.
Okay, so-
For the moment, all right. Now, in fact, there are no gauge invariant things that I can make up just out of the A's that don't involve F mu nu. And I've given you one example. In fact, it is the example that really does give rise to the real Maxwell equations, to take the Lagrangian to be this object over here. The question now is, how do you get the right-hand side of the equation? Where did that come from? You have to add something to the Lagrangian. You must add something to the Lagrangian. That something had better involve the current vector, the 4-component of a current vector. If it doesn't involve a 4-component of the current vector, it's quite clearly not going to give you what you want. So let's suppose that there's some pre-established electric current. That electric current means a charge density, and as I showed you last time, a flow of charge, space and time components. So let's go back and recall the principles of charge conservation first, before we do anything else. We have 4 components, J mu, which equal the time component, which is charge density, and the space components. And remember what the space components are. The space components are the charge per unit area per unit time passing through a little window oriented along the m-axis. The charge flowing through a little window oriented along the m-axis or perpendicular to it, the charge per unit time per unit area, and that's called the J. Okay? The rule, if you take a little cell and you say the charge in there, of course the charge in there is proportional to rho times the volume of the, it's rho dx dy dz. That's the charge in there. And the rate of change of the charge in there is just the time derivative of rho times dx dy dz. If you say the only source of change of the charge in that region is charges which pass through the walls of the region, okay, then that gives you the continuity equation, and the continuity, we worked it out last time, is rho dot, that's a change of charge in a little cell, plus del dot J equals 0. Del dot J means partial of Jx with respect to x, plus partial of Jy with respect to y, plus partial of Jz with respect to z. All right. So to read this, this is the change of charge in a little infinitesimal cell. This is the difference between the charges, or the charges passing out through the x windows. This is the charge passing out through the y windows, and so forth. And this is just the balance of charge inside the box passing through the boundaries of the box. All right, we can also write this in a relativistic notation, d mu j mu equals 0. D mu j mu equals 0. Okay, that's the equation. It's called the continuity equation, but it represents charge conservation. It represents the idea that no charge disappears unless it's accounted for as moving out of the region. Okay? And in fact, if you want to know where that charge went, you go to the next box, and you discover that the current passing through this window over here just adds charge to the next box. So the charge that disappears in this box goes into the neighboring box. And that's charge conservation. All right, now, given the continuity equation, there's another term, another gauge invariant thing. It's a scalar, and we can write it down involving the vector potential, and we'll check and see if it's gauge invariant. It doesn't look gauge invariant to begin with, but we'll see that it is. The action associated with the current, as usual, is the integral of d4x of some kind of Lagrangian. And I'm going to write down the very, very simplest thing I can imagine, j mu times a mu. This, of course, means j mu of position, space-time position, a mu of position. That is a scalar. It's the 4-vector product of a 4-vector and another 4-vector. That's a scalar. It involves a current, and it involves the vector potential. But it doesn't look gauge invariant, does it? How can we check if it's gauge invariant? Well, we can check if it's gauge invariant. Incidentally, by convention, there's a minus sign in front of it. That minus sign ultimately is due to Benjamin Franklin. And, you know, as I said, it is a convention. Okay. Why is the Lagrangian here is, of course, j mu a mu. Or this term in the Lagrangian is j mu a mu. All right, let's do a gauge transformation. Let's do a gauge transformation. What happens to this? It goes to minus the integral, same integral, d4x of j mu. And now we're adding to a mu. I'm going to add something to a mu. I'm going to add ds by dx mu. J mu ds, this is the change. All right, what is this? This is the change in action under a gauge transformation. Under gauge transformation, GT. That's the change. Doesn't look like 0, does it? If it's not 0, then the action is not gauge invariant. But it is 0. Let's check that it's 0. Let's see if we can see why it's 0. The integral d4x, what does that mean? It means integral dx, dy, dz, dt. Let's write it down. dx, dy, dz, dt. All right. Now, we have times j naught ds by dx naught plus j1 ds by dx1, right? Plus dot, 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 dot. And this is integrated over all space. I'm going to make one assumption. I'm going to assume that if you go far enough away, there is no current flowing, that all of the currents in the problem are contained within a big laboratory, so that J goes to 0 far away. If not, if there's a current flowing at infinity, you have to take it especially into account. But you know, for any ordinary experiment in a laboratory, currents move and so forth, charges are there, but you can imagine the laboratory being isolated and sealed so that no currents go out of the box. In that case, let's see what this gives. Let's take a particular term. Let's take the integral j1 ds by dx1. There's one particular term. And now that has to be integrated. x1 means x, dx, ds by dx, dx, dy, dz, dt. Everybody know how to do this integral by parts? Do you know how to do it? There's an integral here. Forget the dx, dy, dz. Just forget that. We're doing an integral over x of j times ds dx. Do you know how to do an integration by parts? The rule is you flip the derivative to the other factor and change the sign. We've done integration by parts many times. I'll just remind you, if you have an integral over x of a thing times the derivative with respect to x, you can do the integral just by flipping the derivative onto the other factor and changing the sign. So this is minus integral dj 1 by dx1 s dx, and then the rest of them dy, dz, and so forth. What would happen if I did the same game with the second term? The second term is j2 ds by dx2. What would happen is we would get another contribution, and the other contribution would be dj2 by dx2. And supposing I did the third term, ds by dx3 times j3, that would give me dj3 by dx3. And finally, there's the time component. There's also a time integration here. If you do the whole thing, you find out that the change in the action is the integral dj mu by dx mu times s. All right. We started out with j times ds dx. We integrated by parts, and that put the derivatives on the j instead of on the x. That's all we did. Did a trick to take the derivatives and put them on the j. That's what we have here. And that's equal to 0 because of the continuity equation. So that's equal to 0. So the change in the action, if the current satisfies the continuity equation, and only if the current satisfies the continuity equation, then adding in this peculiar looking term, where is it? Right here, is gauge invariant.
Does it satisfy the continuity equation, or just you have to have del dot j equal to 0?
No, no. You have to have rho dot plus del dot j equals 0. Okay, let's go back.
That's the first before vector.
Yeah, yeah, that's the first. That's the first. Yeah, that's right. That's the first term here. You have to have all 4 of them, right? Or the sum of all 4 of them is equal to 0. That guarantees current conservation. Okay, that guarantees the gauge invariance of this term. So we can add this to the Lagrangian. Now, what does this do to the equations of motion? Well, we haven't added anything that involves a derivative of A. Right? We haven't added anything. We've just involved something. We just added something that involves A itself. Where's our Euler-Lagrange equations? Our Euler-Lagrange. All right. So our Euler-Lagrange equations have a left-hand side, d mu of partial of L with respect to A nu mu. It's the left-hand side. And the right-hand side is partial of L with respect to A nu. Term by term, component by component, we write down the Euler-Lagrange equation for each component of the field A. On the left-hand side, we know what that gave us. That gave us minus partial of f mu nu with partial of f mu nu. I think it was with respect to x nu. That's what we got from the previous terms in the Lagrangian. What is this one going to give? Well, we go back. Here's the new term in the Lagrangian. What happens if we differentiate it with respect to A? We just say J. Taking this term in the Lagrangian and differentiating it with respect to a component of A, you just get the corresponding component of J. So we get this is equal to, I think, minus J nu. The lesson here, there's a couple of lessons, many lessons. First of all, you can write Maxwell's equations in Lagrangian form. That's important. Second of all, the Lagrangian has a very simple form, minus a quarter f mu nu squared minus j mu a mu. Third, it's gauge invariant if and only if the current is conserved. What happens if the current is not conserved? then the Lagrangian's not gauge invariant, and what you will find out, that's a disaster, because it means that the equations of motion are not gauge invariant. If the equations of motion are not gauge invariant, that's something really strange, because the left-hand side of the equation of motion is certainly gauge invariant. It only involves the electromagnetic field tensors. And so that means something very strange is going on. It just can't be the right equation. It's not the right equation.
Satisfy the continuity? I mean, that's almost like
The continuity equation, yeah.
so it has to satisfy.
Well, that's the conservation of electric charge. You could imagine a world in which charge just disappears. What would happen if charge just disappeared? Well, maybe nothing so terrible, but Maxwell's equations couldn't be right. Maxwell's equations could not be right. You can derive, it's a little exercise, you can derive the conservation of charge from Maxwell's equations. Let's, I don't know, I'll take a risk and try to do it. Try to do it from, let's see if we can derive the continuity equation from Maxwell's equations. All right, so here's Maxwell's equations. Rho equals del dot E, and J equals the dt plus del cross B. Okay, so let's first take rho dot. What is rho dot? Rho dot is equal to del E dot. Right? You differentiate, time differentiate both sides. Okay. What do you think I ought to do next?
Del dot J.
Del dot J. Yeah. Del dot J. Here we have del dot E dot. Here we have E dot. Let's see what happens if we take the divergence of this. What's the divergence of a curl? Always 0. Divergence of a curl is always 0, so let's put del dot, but now cancel this out. So we have del dot J equals del dot E dot. But that's exactly what we have here. So this gives us, I hope it doesn't give us del dot J, because it should be minus del dot J. What happened here? Did I make a mistake somewhere? Rho equals del dot E, and E dot is equal to, is it del cross B? It doesn't matter, plus J? Do I have that right?
Minus del cross B.
That's not going to make any difference. That's not going to help me. I think it's right. E dot, unless I have a sign error there, but I think it's right. All right, let's try it out. Let's see. All right, so rho dot is del dot E dot. That's for sure if rho is equal to del dot E, and that's equal, oh, and that's equal to nothing yet. All right, that's that. Now we have E dot is this, so let's try del dot E dot. The divergence of the curl gives 0, and that's going to give us del dot J. I've got a sign error somewhere, and I'm not sure where it is. I have rho dot is equal to del dot J. Oh. I have a feeling.
Change E and B in the line.
I have a feeling there's a sign error here. I suspect there's a sign error here. I don't remember now. I can't do it in real time right here. There's some sign error here because the right equation has to be rho dot plus del dot J is equal to 0. So I'm not sure what the sign error is, but you can see, apart from the sign error, the conservation or the continuity equation can be derived directly from the Maxwell equations. So, in other words, if Maxwell's equations are true, the charge has to be conserved.
Just looking them up, that, yeah, that should be minus J.
It should be minus J? Yeah. All right, so this is one way, right. Yeah, minus J, okay. All right, so I don't think that affected anything else we said. Right. So you can't have Maxwell's equations and have charge not conserved. That's another lesson. And the final lesson is that the charge conservation is intimately connected somehow with gauge invariance. If it weren't for the charge conservation, and when I say charge conservation, I mean the continuity equation, this one here. Without the continuity equation, Maxwell's equations couldn't be right. Right? So those are the things that go together and that are... Right.
Question?
Yeah.
I'm trying to follow the high order logic.
Yeah.
Last time you gave us a thing about
What's that?
That the continuity equation
Yeah.
came from Maxwell's equations. But then we're trying to prove Maxwell's equations now, and part of that proof, I mean, you're trying to find the Lagrangian for the
Yeah.
Maxwell's equations.
Mm-hmm.
But to do that, we have to have already assumed Maxwell's equations to have the continuity condition, if you see what I'm saying.
Yes, you could have started with the Maxwell equations and said they imply the conservation of charge. Knowing that, you could say, aha, since I know the charge is conserved, I know that there's a term J dot A, which is gauge invariant, and then discover that this is the right term to reproduce Maxwell's equations.
And there's no sort of circularity there in using that reasoning, that's using Maxwell's equation to set up a Lagrangian to prove Maxwell's equation.
Isn't the continuity equation more fundamental than that? It's just
Yeah.
from the definition of current and
Yeah.
charge, right?
Yeah, yeah, yeah.
I mean, you can derive it from Maxwell's equation.
Yeah, you can derive it from Maxwell's equations, but it really just says charges don't disappear. They don't just come and just disappear on you. They only disappear out of a region if they pass through the volume. So these are all connected together. You can start the logic this way and say the basic principle is gauge invariance. That requires J to be conserved, and then use this to derive Maxwell's equations. And in fact, then from Maxwell's equations, you can see that J is conserved, but there's no contradiction there. There's no contradiction there. Or you can start with Maxwell's equations and say, what Lagrangian would give me Maxwell's equations? And one of the things you discover from Maxwell's equations is that J satisfies a continuity equation, and so that tells you, this thing, which I have to put in to the Lagrangian in order to get out the right-hand side, happens to be gauge invariant. So it depends on what you think is fundamental. If you think gauge invariance is fundamental, that tells you J has to be conserved in the sense of the continuity equation. If you think the conservation of charge, that charges shouldn't disappear on you, is fundamental, then the continuity equation is just an expression of that conservation. It just tells you charges don't disappear. And that tells you J is conserved. Or you can think that the Maxwell equations are more fundamental. And again, using the Maxwell equations, you derive the continuity. Things would be bad if they were contradictory. It's good that they and what is the minimal logic? I would say the minimal logic is the combination of gauge invariance, Lorentz invariance, and Lagrangian formulation lead you to this combination, and then you derive Maxwell's equations. But that's a matter of taste. You could have started other places. The fact is things fit. Good. Any other questions?
Yeah.
Yeah.
You showed us gauge invariance mathematically, but it leaves me a little cold. First of all, this word gauge, what are you talking about?
It's a historical anachronism that has no,
It kind of implies measurement or something.
yeah. We're gonna, yeah.
It came from the idea of a gauge, that you have a zero on a gauge. And if you can usually rotate the gauge to change where the zero is.
The zero of what? The zero of what?
Say the zero of pressure on a gauge, or just a mark.
It comes from the idea of gauge pressure.
Yeah, it's just a reference point.
Which is relative to, the pressure that's relative to atmospheric pressure.
It came from a mistake, actually. It came from a mistake which I cannot explain to you now. I can explain to you perhaps, depending on what lecture I give next week, I will try to explain it. But it came from a mistake. The gauge actually had to do with measurements of length. And in fact, gauge invariance has nothing to do with measurements of length. It has to do with measurements of phase, whatever phase is of the Schrodinger wave function. It's got to do with mixing of quantum mechanics and Hermann Weyl made a mistake. He thought it had to do with something that it didn't. He very quickly corrected himself, and the term gauge stuck. But you can, you know, what I think was said was correct. That gauge here meant defining a zero of something. A zero of what? Well, sort of a zero of this scalar field S. But don't worry about it. We'll understand gauge invariance in a deeper way, perhaps next time. It does have a deeper meaning, incidentally. It does have a much deeper meaning, and we'll come to it next time a little bit. Okay, are there any other questions about what we did tonight, though? Yeah.
In the upper left, when you wrote the two families of equations, the one on the left you said derives from the Bianchi identities, and the family on the right.
It is the Bianchi identity.
Right.
Yeah.
The family on the right we got from the
Lagrangian.
equations in motion.
Yeah.
Since E and B are so symmetric, it seems surprising that those families don't seem symmetric. And is there content to that?
You're asking whether they can be interchanged? And yes. Yeah, you can invent a different vector potential with the property that these equations over here become the equations of motion, and these equations with J equaling 0 become the Bianchi identity. So
Another example of a convention we use.
that's not a convention. That was had to do with the absence of magnetic monopoles, which nobody believes anymore. But so yeah. In some sense, it's a convention. Yes, it is this interchange of electric and magnetic it may be that real physics does have an interchange symmetry between electric and magnetic, electric charges becoming magnetic charges. Now, it's not really a symmetry, because if it was a symmetry, we would have discovered those magnetic charges already. They would have been similar to electrons. They would have weighed the same thing as electrons if there was a real symmetry between them, and no such magnetic things exist. So it is not a symmetry in the usual sense, but we don't want to go there right now. I'm too tired for it. Any other questions? Okay, we've actually come a long way. We've come through the Lagrangian formulation of mechanics, the Lagrangian formulation of field theory, the Lagrangian formulation of electrodynamics, gauge invariance, Lorentz invariance. That's a lot of stuff. That's a lot of stuff, and as I said, I think the only way to really digest it is to go home with the equations and work them out yourself, starting from step 1 to step 2. So good luck.
For more, please visit us at stanford.edu.